Here we go. Review of some definitions. Review of some definitions. Maybe. A moment. What is a moment? A moment is a small interval of the independent variable containing a value of focus. Okay? Containing a value of focus. Let's call it x equals a. And then we'll say the moment at a. The moment at a to mean that small interval. Okay, so a moment is a small interval of the independent variable containing some independent value of focus, independent value of the independent variable. And then we'll say the moment at a, the moment at a. So we don't mean the value a, we mean a little interval containing a. Okay, review. So then a rate of change at a moment exists if there's a small enough interval in which the rate of change is essentially constant between 2 points on the graph, between two correspondence points. If you essentially have a constant rate of change between 2 points within a small enough interval, then we say that we have rate of change at a moment. So what about a differential? A differential then is in x, is dx, is a little change in x that varies within the moment. Varies within the moment in question. Okay, so this might be worded slightly differently or significantly differently than in the book, but it should be the same ideas as in the book. So it's a variation on these definitions. Anybody have a question? But as we're having these conversations and we're looking at problems and looking at real-world situations, we got to have these ideas have to be in place so that we're not stumbling over the foundational language that we have. Yes, sir?
The value of focus?
Yeah.
Like in the homework problems, we downloaded it, that's 1 point. That's the value of focus?
Yeah, it gave you a vertical line, right?
Right.
And that's where you were zooming in. And you were zooming in and you were creating moments about that, right? Smaller and smaller and smaller moments.
But
yep.
The value of focus is that one corresponding
It is a single value, x equals a. The moment is then a little interval around a. Yeah?
So dx is referred to as a differential only when talking about a moment of the independent variable?
Yes, because when you're talking about it's in the context of a moment. Yes. Other questions? Okay, so I've got another similar but different. So for more review and more to make sure we're on top of this. So we have, suppose the function f relates Usain's distance from the starting line, dependent variable, to the time since the race started. And I'm saying Usain's speed at the moment, x equals 0.4 seconds. So what do I mean by that? His speed at the moment, x equals 0.4 seconds, means what? So it means that there is a small enough interval at 0.4 such that his rate of change is essentially constant. And that constant rate of change is 3.04 meters per second. Okay? And his distance from the start at 0.4 seconds is 0.702. Okay? So now we got 7 questions, and you're going to answer those 7 questions or respond to those 7 questions as pertaining to his distance from the start at 0.408 seconds and 0.413 seconds. Okay? So first you're going to be focusing on his distance from the start at 0.408 seconds. And for that, capital letter A, you're going to go through this list. And you're going to talk through these things, talk about the symbols, how we represent them symbolically, what the values are, where they show up on the graph. Okay? So we're just kind of looking at the whole situation and applying everything we know to these things. And then after you're done with 0.408, then we'll switch it to at 0.413 seconds. And then you're going to go through the list again. Okay, so get someone to talk with as you're working on this, okay? Go. stay up there? Okay, good. Here we go. So what do we need the value of the independent variable is? So there's really two important values of the independent variable here. If you're just talking about at what moment are we looking at? So if we're saying this is the moment at what? The moment at x equals 0.4, 0.4. Okay, but so this is kind of a little ambiguous. So I didn't really specify which value. So there's kind of two values. There's the value at the moment, that's 0.4, and then there's the value at which we want to find his distance from the start, and that's the 0.408. So there's kind of two answers to number one. Depends what you're talking about. Are you talking about at what moment are we looking at, or the time at which we want the distance? Okay, so I'll just go with the moment. All right, the moment. So the value of the dependent variable, say at the moment in question. What's the value of the dependent variable at the moment in question? Okay, f of 0.4, which is 0.702 meters. So I should have clarified 1 and 2 to talk about, so at the moment in question, right? Okay, the differential in x. So the differential in x is our little change in x, okay? And just to emphasize, that is a changing quantity, and I'm trying to show that here. It starts at 0, and then that differential in x changes. It changes, okay? So it's, but we're just gonna then, knowing that it changes, we know that at one moment, at one time, at one exact time, it's 0.408 seconds. So what is the differential then in x when x equals 0.408? 0.008 seconds. And then what's the differential in f? Or df? How would you find it? You've got the differential in x, 0.008. We worked hard on this. Who learned something? What's the differential in f? Or how would you get it in the back? Right. The differential in x is then going to be m dx. And we spent a day or two, or at least, on the idea of constant rate of change. If you have constant rate of change, the change in your dependent variable is the constant rate times the change in your independent. So it's going to be that 3.04 times 0.008. And then that equaled to what? He got 0.243 meters. Agree with that? So that's our differential in f. It's the corresponding change in dependence that corresponded to this change in independent 0.008. Okay? So now, the moment in question. So how would you describe the moment in question in this situation? Somebody knew. What would you say the moment is? Is it dx? Is it smaller than dx? Is it bigger than dx? What do you think? Remember what we said, dx varies within the moment. And so the moment is basically kind of, it's in the context of what I'm showing you here in this right graph. Anybody? Yeah, please.
From 0.4 onward, just until 0.408. That's a key fact, but just continuing from 0.4 until.
Okay, that would be okay for A, but then you're specifically saying that the moment is dx, right? The dx's differential varies within the moment. So we could also say like, for instance, 0.395 to 0.42. Right? It's the moment we're looking at, we have, for this particular moment, we got it so that it's small enough, so we have essentially a constant rate of change. And so it's kind of like the whole interval that I'm showing in this right graph. So from you could have a different answer, but like say from 0.395 to 0.42 would be a decent answer. But he said starting at 0.4. So if you said from 0.4 to 0.2 or from 0.4 to 0.415, that could also be the moment. Okay? But you don't want it, it's not going to be something small like from 0.405 to 0.41. It's not going to be that because dx varies inside the moment. Okay. Yeah.
Does the entire moment have to have a constant rate of change, or is it just from dx until the point you specify?
If you're talking about rate of change at a moment, then the moment has to be small enough so that there's a constant rate. But you can talk about a moment in which it's not essentially a constant rate. But if you're talking about the rate of change at the moment, then that has to be a small enough interval so that you have essentially constant, the rate of change. Is that? Yeah. What else? Okay. So Usain's distance from the start. How would we symbolically write that? So what symbols would we use to denote Usain's distance from the start? Yes, sir? No, his distance from the start. How would we write that symbolically? What symbols would represent his distance from the start, 0.408 seconds after the start of the race? We better know this. Do you know? Do you know?
Could it be like f of 0.408 minus f of 0?
Yeah, but you don't have to have the f of 0. It's just the output of the dependent variable of the function is defined as his distance from the start. F relates his distance from the starting line. See, it's not a change. This is the dependent variable. So all you need is that. It wouldn't be wrong to say that, but you don't need the minus f of 0 because the dependent variable of this function is defined as distance from the start. And that's what we're asking. What is this distance from the start at 0.408 seconds? So I'm just going to believe that you were all thinking that, but not saying it. We got to know function notation. Function notation expresses a value of the dependent quantity given a value of the independent quantity after 0.408. And how would we calculate that? This distance from the start. How about someone up in the back on this side? What would I write to calculate that distance from the start at 0.408? Yeah. Okay, m dx. Is that his distance from the start? Not quite. How are we going to get his distance from the start? What is m dx? His change in distance. So now his new distance from the start, how would we get it? If we got his change in distance, plus, symbolically, f of x? Not f of x. F of x is all the output. Oh, you guys. So if we want his new distance from the start, this is his change in distance. What are you going to add to get his new distance from the start? His change plus? And what's the initial? 0.702 expressed as f of 0.4. Okay, his initial distance at the start of that interval plus the change in distance. Okay, and that M we calculated. This is DF. So this essentially is it is DF, and that DF is 0.243 meters plus F of 0.4 is 0.702 meters. So the new distance from the start is 0.945. Okay, so make sure you get this and can do this yourself. A new value of the independent or the dependent quantity is the original value of the dependent quantity plus the change. Plus the change. So all these symbols should make sense, and it should make sense why we're doing that calculation to get his new distance from the start, 0.945. Anybody have a question? So this is what I suggest. Sleep on it, and then go back earlier in the video where none of this stuff is written down, and you do it all again for B, without peeking at this. So maybe this weekend, Saturday or Sunday, go back to the video where the screen is all blank, and then you work through B yourself. Okay? Really important. Yeah. This is a video. Just go to the video where it's blank. Yeah. Question? Did I make a mistake? This little change is 0.0243. Okay, yeah, this brings me up to something else. So part of your homework was to correct my mistakes at the end of last lecture. Please, please, I'm begging you with all my might, if I make a mistake, thank you, speak up. Okay, if you're looking at that going, I don't think that's right. Yes, I make mistakes, like sometimes more than one in a week even. Okay? It really does happen. Please, I'm begging you. And so the worst thing that can happen is that we just have a discussion and it was right. And I appreciate that you thought, that you spoke up. But don't let me sit here and dig a hole while half the class is like, I don't think that's right, and no one's saying anything. The other class is just like so asleep that they didn't even notice. Okay? So, please, one more time, I'm begging you, if I make a mistake, we need to have an extra credit system for that. Yes, sir? Okay, shh. So this is supposed to be 0.0243. Okay. And then this is supposed to be 0.0243. Thank you to the brave soul who spoke up. And so now this is not 0.945 meters. What is it? 0.7263. Those who are paying attention, is this what you got? Does it make sense? Are the numbers right now?
I think we skipped number 6.
Yeah, probably. That's an easy one. What's the rate of change at this moment? 3.04 meters per second, right? And it's because in this interval, the graph is essentially linear, and I told you that the speed at this moment is 3.04 meters per second. So yes, right. 6 is 3.04 meters per second. Okay, other questions? We're not going to do B. I want you to go sleep on it, let this fade a little bit, and then you work through B again. This is all really important stuff because next week and the following week, this is going to start getting hard. Okay, this is the easy stuff, and it's going to get hard fast. Yeah. MDX. The change in F? Yes, but you don't know that's what we're trying to find. We're trying to find F of 0.408. So you can't calculate the change in F with something that we don't have and we're trying to find. You see? I didn't give you the function. I just told you here's the rate of change and here's a time and a position. So now you're going to predict what his position will be later. So you can't calculate dF that way. You need to use constant rate of change to do it. The change in dependent is the constant rate times the change in independent. And we spent a long time toward the end of exam 1 working on examples, snack mix and the flag, and we did a lot of this, so don't forget that. Okay, other questions, comments? Okay, so can we always zoom in enough to get a rate of change in a moment? And you learned that in your reading. The answer is no. Does it have a rate of change at the moment x equals 2? Sure looks like it. How do we know for sure? Zoom in, and if you zoom in and for a small enough interval, it's essentially a constant rate of change, then we have a rate of change at that moment of x equals 2. Is there a rate of change at any moment in this graph? No, there's a. Yeah, I think this is x equals 1, y equals 2. What happens if we zoom in on that? Well, isn't the rate of change 0? What about just before 1, for a moment right before 1? Does the rate of change at a moment exist? At a moment right before 1? Yes. And what about right after 1? Yes, we can zoom in and get a small enough interval that we would have essentially a constant rate of change. But if we're talking about the moment at 1, it doesn't matter how far we zoom in. A constant rate of change does not exist because there's this abrupt change in rate of change. See that? At 1, the rate of change changes abruptly. So here we say there is no rate of change at the moment 1. There is no rate of change at the moment 1. But what about at 0.9999? Is there a rate of change at at the moment 0.9999? And 1.00001? Yes. Okay. But if we're talking about at the moment 1, x equals 1, the rate of change does not exist. Okay, and then you guys read about and you looked at things that we're referring to as wrinkly functions. So here is number 5. Number 5 in the homework. So let's talk through this one. So this is the idea of a wrinkly function, that in any given interval, it seems to what? It seems to have wrinkles, okay? Or it seems to jump and not have, at this particular view, you look right here and you say, is there a rate of change at that moment in this view? Well, we don't know, but it certainly is possible that there's no rate of change there at that moment because it looks like a cusp. It looks like a corner point. But then the graph is filled with those, right? It's like there's tons of these places where there's potential cusps. And maybe there are some, okay? But so what do we do? We need to zoom in and find out what's going on here. All right, so if you studied you've worked on these for a couple of nights now, what does the pink arrows represent? So those pink arrows, what do they represent in this situation? The moment? No, it's not the moment. It's a differential in x if you look. when you change dx, so I'll make it 0.0, now it's right now it's 0.01, make it 0.02, what happened? Just doubled. So this is looking at dx, actually 2 times dx. So from the point in question to here is dx, and then there's dx going out the other way as well. Okay? So what are we doing? We're looking for a interval small enough so that we can find out if this is essentially linear in a small enough interval. So we keep zooming in. And what is the purpose of the red line? What is the red line? What did you discover about the red line? It references what? Okay, can we say that in mathematical terms? It's a reference of what? What is the red line a reference of? Yeah, it ends up being a reference of the constant rate of change at this moment. It sure doesn't look like it, right? I mean, if you were to guess right now, what would you think? It's not even close, right? You would think, oh, this is the constant rate. But when you zoom in, did I screw something up here? I didn't change anything, I promise. Let me start over here. I just did this before class. Let's see. Okay, I'm going to start over. I don't know what happened. Okay, let me try again. Okay, there we go. So notice it starts to look like it's flattening out, and then you zoom in further, and then there's more wrinkles, right? It's like the more you zoom in, the more wrinkles you see. There we go. So I'm going to just show this much. More wrinkles. You see this? So I'm going to show just this much. More wrinkles. But eventually, we get to a place where what is wrong with this? It just worked.
Gone too far.
Gone too far. Okay, so what's wrong? Anybody know what happened? What's that? Oh, I have to adjust my dx? Because is the red line... Look, okay, here's what's going on. Look, the red line is graphing in terms of m, which is in terms of dx. So it's still graphing, this red line is still graphing according to a dx of 0.01. That's why it's not, so I gotta adjust my dx. Do you understand? Until our dx shows up on the screen, even more. Come on, where are you? There it is. Okay, so maybe I went in further than I need to, but it works. Okay, it works. So I have an extremely small dx, and you see that the function is essentially constant for this dx, and so therefore the rate of change at the moment exists, and it looks pretty close to 4. Looks pretty close to 4. Okay, so then there are functions that you read about that are so wrinkly that no matter how much you zoom in, you never can get rate of change at a moment. You just keep zooming in, and there's just always wrinkles forever and ever, no matter how small you make your intervals, right? And we call those infinitely wrinkly functions. Infinitely wrinkly, and they're only possible using the summation, right? Using the summation. So they're functions like this. They're functions like this. So let's show the original. But no matter how much you zoom in, you always keep getting wrinkles. And so there's never a rate of change at any moment in the whole graph. Okay? Now, so this is a wrinkly function in which you do eventually, at least at this point, but at other moments, there may not be a rate of change because there's a cusp. Okay? But at this particular moment that we zoomed in on, we eventually, with a small enough moment interval, the graph is essentially constant, and we got a rate of change. Okay, so take a couple minutes to talk to the person next to you about big ideas today, and then we'll have Top Hat in a couple minutes. Go.